Hello, we're going to be looking at the very clever asymmetric encryption in this video. But let's start by talking about symmetric encryption for a second, because there is a problem with symmetric, which explains why asymmetric was invented. This is called the key exchange problem. As a recap, symmetric encryption uses the same key to both encrypt and decrypt your data. So that key is really, really important. If I'm wanting to exchange data, as in send it to somebody, using symmetric encryption, how do I share this key securely? It's not obvious how I can do this. If I'm just storing it on my computer, that's not really an issue because only I need to know the key. But if I'm exchanging data, the person I'm sending it to also needs to know the key. And how do I get this to them securely, right? I start with some plain text. I want to send the message, hello. I create a secret key. I use some symmetric encryption algorithm to apply it, maybe AES or something similar, to give me some ciphertext. I send the ciphertext to my friend, but without the key, they're not able to understand what this ciphertext is representing. So what I need to do is find a way of sending this key to my recipient. I can just send it over a public network, which would be all right for my recipient. They'd be able to then use it to decrypt the data, see my original plain text. However, an attacker could be sat intercepting the messages and they'd be able to see this key in plain view. And if they were looking at your whole history, they might be able to figure out that actually this is a key for some ciphertext, then they could decrypt it and see the message as well. If you were really concerned about your security, you wouldn't do this. You wouldn't exchange the key over a public network. You'd have to do something old-fashioned, like go and meet the person and share it when you're sure nobody else is listening into your conversation. You have to do things like that to avoid sending it over a network. Because of this, and because the old-fashioned methods aren't always feasible, asymmetric encryption was developed to solve this key exchange problem. So instead of using one key, asymmetric uses a key pair. So one key is used to encrypt and the other one is used to decrypt. And the two keys are called the private key and the public key. The private key needs to be kept secret in the same way that a symmetric encryption key has to be kept secret. The difference here is our public key can be available to anybody. There is no risk to this public key being seen by an attacker. Now, before we look at how this works, I think a bit of context is useful. It's not essential for A-level to learn this off by heart, and it's very complicated, but to get a sense of how this works, I think is really helpful. So a real-life asymmetric encryption algorithm is RSA. There are a few other ones. There aren't as many asymmetric ones as symmetric ones, but RSA is one of our most well-known ones and was really the first one. So RSA relies on the fact that it's very easy, or relatively easy, to multiply two prime numbers together to give a result, but very, very, very hard to then take this result and then factorize it to give our original two prime numbers. So this is almost like a one-way function. I can multiply the two numbers together really quite easily, but to go backwards, it's almost impossible. And a computer cannot do this efficiently at the moment. And this fits quite well with encryption because we want to be able to encrypt data relatively easily, but for someone to decrypt it without a key should be very, very difficult. One interesting thing to know is that asymmetric encryption tends to have a lot longer keys than symmetric encryption. So asymmetric encryption might have over 2,000 bits per key, if not a bit longer, whereas symmetric might only be a few hundred bits. This is because the key is linked to how big these numbers are, and we want our numbers to be really, really big. So if we're going to run RSA, we're going to avoid all the complicated maths because we don't need to know it, but the numbers involved are massive. The first step in generating the two keys is to get two random massive prime numbers. These are two real random prime numbers, which are huge. It's really hard to comprehend how big these numbers are. And as part of the algorithm, a computer will multiply these two numbers together, which will take a second or two, but is not very hard for a computer to do in the general scheme of things. What is very, very hard for a computer to do is take this long number and work out what the two original numbers were. It just takes an extremely long time, which is why this encryption is secure. To skip some of the details, we take this product, and from this product, we can generate our key pair. The private key tends to be a lot longer than our public key, but they are mathematically linked to each other. So these aren't two random keys I've just created. They are intrinsically linked together because of the product of those two prime numbers. Because of that massive product being really, really hard to factorize, that means this encryption is hard to crack without the key, And because these two keys are linked, in order to be able to do the whole process, you need to know both keys. And the whole point is the private key is kept secret, the public key is available for anybody to see. And we'd use these two keys to either encrypt or decrypt our data. How that is done using RSA is a whole different method, but this is how we get to the first step, which is having keys I'm able to use. So I'm showing you that really for context with how big some of the numbers here, but also it's important we realize that there's a mathematical link between our private key and the public key, which means we can encrypt and decrypt using the other key, which is really, really important. So to take a more easy, high level understanding here, we can look at what we definitely need to know for A level. So we can use asymmetric encryption to send a message securely without any issue with key exchange. So let's say I've got my bank on my right. I want to send a message to my bank securely. For example, my password is obviously compsci123. I want to send this to the bank securely. Well, how do I do this using asymmetric encryption? Well, before I even begin, the bank needs to have generated its key pair using the maths we just briefly touched on. So these two keys are linked together and are a pair. This private key is kept secret within the bank and nobody outside of the bank should be able to see it. Really, in reality, no human should be able to see it. It should be kept locked away somewhere in a server, lots of security. The public key, on the other hand, can be publicly viewed. And if you want to go on any website now with a padlock, you can see their public key by clicking the connection is secure and looking at what's called the certificate. It will show their public key for anybody to see. So what I would then do as a user is I would then encrypt my plaintext, compsci123, using the bank's public key. This would create a ciphertext, which I can then send to the bank. What we said earlier was that one key is able to encrypt the data and only the other key is able to decrypt it. Because I've encrypted it using the public key, only the private key is able to decrypt it. So I've used a minus sign to represent we're decrypting now, but I'm able to use, if I'm the bank, my private key to decrypt what the user has sent me so I can see that actually they sent me compsci123. If I encrypted it using the public key, I cannot then also use the public key to decrypt it. So an attacker also can see that the public key of my bank is 789. But if the attacker intercepted my ciphertext and tried to decrypt it using 789, it would get either nonsense or more likely an error because it just doesn't work. Mathematically, it won't work trying to reverse it using the key used to encrypt it. Now, this is the main use of asymmetric encryption, for one which you have to really get your head around and really study. So this is the one to focus on. To give you another application of it, which is a bit more confusing, but is just interesting to understand, is we can also use asymmetric encryption to verify a sender's identity. So I can use asymmetric to make sure I'm actually communicating with my bank and not an attacker. So to use the same setup, we've got this private key, which is kept under lock and key. Public key is available. This time around, the bank is going to send a message to my user. So it'll be a more formal message. They'll let the user know this message is going to come and what it will say. But they'll send a message which is encrypted using their private key this time. This time we're using the private key to encrypt, not the public key. We still get some ununderstandable, unintelligible ciphertext, which is sent to our user. The user will know the bank's public key is 789. So therefore they will use 789 to decrypt this message. And because it was encrypted with a private key, the public key is able to decrypt it. And we will see the message in plain text. Therefore we can trust that the bank was actually sending this because only the bank could have sent that message because of the public key and private key being linked mathematically. These are a key pair. As long as that private key does belong to the bank and is secure, we know that it must be the bank communicating with us. And it seems a bit flawed because ultimately an attacker could still be intercepting this. At this point, it is ciphertext, but it's not very secure ciphertext because the attacker could just decrypt it using the same public key that my user can see. Right? The attacker can see the same thing that I can. They can also decrypt it. But the point is this message here isn't a secure message. It's just a kind of placeholder message allowing me to double check the person sending it is who they say they are. I don't really care if the attacker can see this message. I only care that I can verify that it was the bank. To look at an example of where an attacker might be trying to pretend to be an organization like your bank, well, let's assume the public key for the bank is still well known and is still trusted, and we've got no issues with the public key. It's still 789. Well, the attacker doesn't know what the private key is of your bank, so it's got to create its own one, which is almost certainly going to be different to what the bank used. Because it's different to what the bank used, it won't be connected to the public key in the same way. So despite the attacker trying to use the same message and create ciphertext, this ciphertext won't decrypt using the public key, which is what the user is expecting to be able to do. The user thinks this message is from its bank. It will try and decrypt it using the public key, which is well known, but it just won't work because they're not mathematically linked. This public key wasn't generated with this private key. Therefore, we know this is being sent by an attacker and not being sent by my bank. So just to clarify again, this is kind of a secondary use of asymmetric encryption. The primary use is to send messages securely. This is just another helpful, almost side effect of it. Now, we have got a choice whether we want to use symmetric or asymmetric encryption. Well, what are the pros and cons? So symmetric is faster to encrypt or decrypt than asymmetric. The maths involved is still very complicated, but it's not quite as computationally expensive as asymmetric is. So it's faster to do. And symmetric encryption, we have to create a key, but it's only one key and I can just create whatever key I want. Asymmetric, we can't just create any keys we want. We need to generate two keys which are linked together mathematically, which takes a bit longer to do as well. As I mentioned earlier, asymmetric requires a longer key than symmetric to be secure. This isn't about brute forcing, because to brute force a symmetric key, which is maybe 128 bits, is very, very long, let alone the 2000 bits that asymmetric needs. It's not really about brute forcing, it's more about the numbers involved. For the asymmetric maths to work, the numbers have to be massive, which means the keys are long as a consequence, which takes up more storage space to store these. However, the key reason why we might use asymmetric is because we don't have to share a key securely. Public key can be shared, but it doesn't need to be shared in a secure way because we want everybody to be able to see my public key. This private key is kept secure, but it's not shared with anybody. So we use asymmetric when we're communicating over a network almost always, whereas symmetric would almost always be used if we are just storing stuff on one computer and only I need to know the key. However, this being said, we can still be clever and use a hybrid of these two approaches to get the best of both worlds when communicating. So if I'm still wanting to communicate over a network, I might want to initially generate a symmetric key. Then I can use asymmetric encryption to exchange this key securely. So I'll use my recipient's public key to encrypt this symmetric key, send it to them, they can decrypt it using their private key, and then from now on, we can use the symmetric key to use symmetric encryption because both of us know the symmetric key. So we almost use asymmetric just as a starting point to exchange the key. We then switch to symmetric because it is a lot faster to use.